Okay, let's dive into this. Welcome to the Explainer. Today we're going to unpack one of the absolute most critical decisions in all of machine learning, how we actually hire the right AI for the job. You see, it's not just about, throwing data at a computer and hoping for the best. It's actually a highly specific, kind of fascinating matchmaking process.
But we've got to start by addressing a super common myth. Is there a master algorithm out there? I mean, really think about it. Is there one single, perfectly tailored candidate that can just walk into any server room, glance at any data set, and do every single data job perfectly?
Well, the definitive answer to that question is a hard no. There is no single best algorithm for every data set or every problem. Let's just bust that myth right out of the gate. The core thesis of our entire explainer today is that model selection isn't about finding the objectively best algorithm in the world. It's a highly contextual matchmaking process.
To help guide us through this matchmaking process, here is our roadmap for today. We've got 1. The best algorithm myth. 2. Matching models to problems. 3. Complexity in desired outcomes. 4. How data drives performance. And finally, 5. The power of comparison.
All right, Section 1, the best algorithm myth. Let's clearly separate two completely distinct but connected steps. And hey, you'll definitely want to lock these in if you're prepping for an exam. Model selection is the act of choosing the most suitable machine learning approach for your data and the task at hand. Model comparison, on the flip side, is evaluating those alternatives to see which one actually performs best for your specific goal. Basically, selection is building the shortlist, comparison is the actual interview process.
And this perfectly explains why the exact same dataset can give you wildly different results depending on the model you pick. It's because different algorithms essentially have completely different resumes. They learn in entirely different ways. Some are incredible at spotting linear relationships, while others prefer splitting data into decision rules or finding local similarity patterns. If you have highly nonlinear data and you hand it to a simple linear model, it's going to underperform. It's literally just the wrong tool for the job. Let's move to Section 2, Matching Models to Problems, and see how this builds. Think of this as our job description matrix. It all starts with a really basic question. What kind of outcome are we actually trying to learn? If we're doing continuous prediction, like, say, guessing a numerical price or a test score, we'd pair that with a candidate like linear regression. If we're doing categorical prediction, like a straightforward yes or no label, we might choose a decision tree or k-nearest neighbors. But what if the groups are totally unknown and unlabeled? Well, then we bring in a clustering algorithm. And for complex spatial patterns like recognizing faces in photos, we hire a convolutional neural network, or CNN. We are actively, intentionally matching the AI candidate to the structural reality of the problem.
Moving right along to Section 3, complexity and outcomes. But what happens when the job requirements clash? And this brilliantly illustrates a classic trade-off in machine learning. On one side, you have the desire for high accuracy. To get that, you often need highly flexible, incredibly complex models. But the trade-off? They're computationally expensive and way harder to interpret. They essentially become these mysterious black boxes. On the other side, you have high interpretability. These are simpler models that catch simpler patterns. They're super easy to explain, lightning fast to run, and much cheaper computationally. The catch is, you usually can't maximize both of these at the exact same time.
Let's ground this in the real world. Imagine you're running a hospital, right? You're deploying an AI to help diagnose your patients. Now, a highly complex deep learning model might offer the absolute highest accuracy score possible. But doctors need to know why a diagnosis was made. They need interpretability to actually trust the decision and explain it to the patient. So in this real-world scenario, the hospital may deliberately choose a slightly less accurate but highly interpretable model. Because in healthcare, the explanation is just as critical as the raw prediction itself.
Okay, Section 4, how data drives performance.
Listen, even the most qualified candidate will completely fail if you drop them into a toxic work environment. And in machine learning, that toxic environment is messy data. Imagine a data set where 99% of the examples belong to Class A and only 1% belong to Class B. We call this imbalanced classes. If you build a model to predict Class B and the model simply decides to guess Class A every single time without learning a thing, it's still going to be 99% accurate. That high accuracy score is incredibly misleading. This is exactly why you absolutely cannot judge a model's performance without fundamentally understanding the character of the data it's processing.
So what are the properties of a dataset that actually influence that performance? Well, they include the overall size of the dataset, the amount of noise or errors hiding in there, the number of features or dimensions, the class balance we just talked about, and just general linearity and complexity. A model that performs beautifully on clean, simple data might completely fall apart when the real data is noisy or high-dimensional. The data itself dictates which algorithms even deserve a chance to be tested. Which brings us to our final stop, Section 5, the power of comparison.
This is why we absolutely have to put our AI candidates through a trial shift. So, the crucial point is this: performance must be tested, not assumed. If we skip the comparison phase entirely, human bias creeps right in. We might pick a weaker model just because it's an algorithm we're personally familiar with, or maybe because it's easier to code up. Comparison forces us to be objective. It completely transforms model selection from a hopeful guess into a rigorous, evidence-based process.
So what exactly does this trial shift reveal? Well, it shows us the real-world accuracy, sure, but it also shows us generalization, meaning how well does the model handle completely new, unseen data? It reveals performance stability, and, crucially, definitely flag these terms for your exams, it detects overfitting, which is where a model practically memorizes the training data but completely fails in the real world, or underfitting, where it's just too simple to learn anything useful at all. Comparison gives us the hard, undeniable evidence we need to justify our final choice.
All right, let's pull all of this together into the ultimate AI matchmaking checklist. Seriously, consider this your definitive study guide. Number 1, what is the nature of the problem? Is it continuous, categorical, or unknown? Number 2, what is the problem's complexity? Do we need simple lines or deep, complex flexibility? Number 3, what is our desired outcome? Is accuracy everything, or do we desperately need speed and interpretability? And finally, number 4, what are the specific data characteristics? Is it noisy, imbalanced, or clean? I want to leave you with this provocative thought to really apply what we've covered today. Would you choose the exact same machine learning algorithm to run a school grading system predicting at-risk students as you would to generate a life-or-death medical diagnosis for doctors? Think about the stakes, the need for explanation, the complexity of the data, and those real-world outcomes. Once you understand that those two scenarios require entirely different AI candidates, you truly understand the art and science of model selection. Thanks for exploring this with me.